Hello, hello, coming up on 3 minutes to start. Quick mic check. Um, Anyone can post a quick chat message. You can hear the music and me. Okay, quick 1 minute check. Someone please post that you hear me. Otherwise, I have technical problems. Do I? Nice, great, thank you. Awesome. Sorry. My software says that everything's live, but you never know. All right, give it a couple of minutes. People to join. Nope, you can't drink my water. Hey everyone. Hey everyone. All right. Okay, Google, stop. And let's get started with lecture 12 for EECS 281. Welcome back, everyone. This is the last major topic before the exam, Mergesort. So it's one of the efficient algorithms that we'll be discussing. We already discussed as far as efficient algorithms for sorting goes. We have discussed heap sort and quick sort, and then this third one, merge sort. Okay. So a reminder that you should be signing up for which time slot you will be taking the exam on, the midterm. So make sure you fill that up. All right, so let's get started. You've actually heard me refer to Mergesort quite a few times before. So today we'll look at it in detail. So some good news is the fact that a big part of the code needed to implement Mergesort, you've kind of already seen before when we were discussing ordered sets, I think 3 lectures back. And we discussed implementing an algorithm for doing the union of 2 sorted ranges. And we had code there that implemented that using iterators, if you recall. So we're going to revisit that functionality in the context of the Mergesort algorithm, and in fact give you a much more compact version of that same code. All right, so let's get to it. If you recall from the last lecture, quicksort kind of works by dividing a file into 2 parts, or I mean, our example was in the context of arrays, really. And basically we had k smallest elements, right? And then we had a pivot value that we would use to determine those k smaller elements, and then n minus k largest elements, okay? So Mergesort combines 2 ordered files to make 1 larger ordered file, right? And this goes back to, again, when we were merging 2 sorted ranges. The algorithm is a combine and conquer algorithm as opposed to a divide and conquer. It's just nomenclature, really. As far as algorithm families go, they kind of fall in the same category, but the distinction is that quicksort is more of a divide and conquer, and Mergesort is a combine and conquer. Let's see really what that distinction is in terms of pseudocode, right? So quicksort is effectively more of a top-down algorithm, whereas Mergesort is the opposite. It's more of a bottom-up approach, right? And what we mean by top-down approach is that for quicksort, for example, right here in this oversimplified pseudocode from what we saw last time, we first do a bunch of work, which is the partitioning, followed by then doing the dividing, which is the recursive calls that we have here, lines 3 and 4. Okay. By contrast, Mergesort actually does the dividing first, right? These 2 lines of code really do no work. Oops, my pen suddenly quit on me. I don't know what it's not working, right? Give it another shot. Oh. Make sure it's sync up with my iPad. All right, well, my pen is quitting on me. Try to use my finger. Pinky finger. All right, so these here are basically just recursive calls. So you see the algorithm immediately goes into recursive calls to basically get down to the nitty-gritty, if you will, of determining what elements it's actually going to combine. And then as it comes back from all those recursive calls, that's when it's actually going to do the work, which is the merging. Okay? Actually, using the finger is not as bad as I thought. So really no work gets done until you get to the merge function, which we're going to talk about in the next couple of slides. Let's really just look at an example. It's kind of easiest to see when it's an example. So suppose that we're trying to do a merge sort on this input set of integers. Okay. If you recall from that pseudocode, first we would recurse on the left-hand side, right, of the array. We just split it right in the middle. But then remember that recursive call, it's in itself going to immediately go into a recursive call on the left-hand side of this subarray right there. So that gets us 5 and 2. Okay. And then yet again, all it's going to do is go into a recursive call to just get us 5. Okay, which is the 1/2 of the 2-item subarray. And then that's going to finish the recursive call to then go into the right-hand side of, let's call this level 1 and level 2. Okay, so now we go into the right-hand side of the level 2 recursive call to then get 2. Okay, and that is effectively a base case in which merge is just going to look at the 2 elements and then merge them together. Okay, so this is when this would be merge. No, it's not as easy to write here with the finger. Let's see, my pen now works. Well, it was working a minute ago. I'm not sure what's the deal. This, I'm going to use M for merge. So it's easier to write. Merge. That's what was merged. Okay. All right, so at that point, it has finished. If it will come back from all the recursive calls in the left-hand side of level 1 recursive call. So then it'll look at the right-hand side recursive call at level 1, which will look at the right half of the subarray at level 1. But then again, it's going to split first the left-hand side, followed by splitting and looking at the left-hand side, which is just one element on each side. So the merge is pretty simple because it's just merging 2 elements to come up with a merged subarray of 4 and 7. Okay. At that point, it is done with this side. Oh, so now we would be merging right here. Okay. And at that point, it will look at the right-hand side at level 0, if you will. Okay, it's right here. And so in that right-hand side, we will look at the left-hand side, which is 1 and 3. Continue to look at the left-hand side. Then at that point, there's no more recursive calls. So come back 1 up and look at the right-hand side. Now it's time to do a merge. So it'll merge that pair of elements. Okay, done at that level. So move on to level 1 and then split on the right-hand side. Rinse, repeat to now come up and merge 1 and 6. As you see, the merge is really simple. It's 2 elements, similar. And now I can go ahead and merge at that level. So that's another level of merging right there. And then all that recursion would come back up and then hit the merge function to then merge everything. Okay. So fairly simple. As you can see here, we have the key 1 is repeated. Okay, you have the underlining of the second key, so it's easy to spot where each one of the ones sits in the subarrays. But as you will see, there is no way in which we would ever shift the one that's to the left-hand side, which is underlined, and have it swapped so that it goes before the number 1 that's not underlined. So that's kind of hinting at the fact that Mergesort is stable, which I think was a question that was asked in the last lecture was, if I want stability and efficiency, which algorithm we could go with, and that is Mergesort. Okay, so that is stable. Okay. All right, so we've kind of discussed pseudocode and an example of kind of how it works. Not a terribly complicated algorithm. You could say that quicksort is, a tad more complicated than Mergesort. The considerations for when to use this algorithm, it does kind of have a downside, and as we're going to see, is that in its simplest implementation, it uses extra memory, and that is what we're going to discuss today, is the implementation of Mergesort that does use linear amount of extra memory. Okay, linear in the size of the input size. Okay. There are versions of Mergesort that are in place, but they're really complicated to come up with. And you think of a way to reuse the input array rather than to use an extra array, but it can get quite tricky. And there's so we don't really discuss it in this lecture in detail, but you're free to look it up. Again, it would be built on swaps because, again, with swaps you would be trying to reuse the input array. The main assumption that we're going to make when discussing Mergesort is that we will have enough space to create that additional copy of the elements in the input. Okay. This is oftentimes not too bad, largely because Mergesort, one of its main use cases right now is in big data. I don't know if you're familiar with that buzzword, but big data is basically computing that you do at the kind of terabytes and petabytes level, right? So it's enormous amounts of data. If you want to buy computers that have that much RAM, it would be ridiculously expensive. But it's fairly cheap to store all that data on disk. Okay, and so Mergesort is very easy to parallelize and distribute, right? Because it doesn't require that all the data be in a shared memory, right? Since all the data is in disk, then you can have a distributed version of the algorithm where you have some nodes that'll look at a chunk of the data in disk, and then another set of nodes that'll look at a different chunk of data. So that's another big advantage of Mergesort. If anybody has heard of Hadoop, which is kind of a processing engine and runs on for big data platforms, the way that it would look to sort petabytes of data is Mergesort. Okay. All right. So, but that's enough of pseudocode and talk. Let's start looking at actual code. Now, before we jump into an implementation, let's take a look at the shorthand notation in C++. You might or might not be familiar with it. It is a ternary or operator where basically it's an if statement inlined, right? And it's just syntactic sugar shorthand notation for the bunch of lines that you see here. You can really just implement inline with something like this. Okay. So I'll let you sort through that. All this is doing is basically if the a at I is less than or equal to b at j, then I basically move that value from a and put it in c, and then increment the pointer, which in this case is just an integer I. So again, and then there's an else. So all of that is inline right here. Basically, your if amounts to this question mark right here. Okay, and this is if this comparison right here is true, we would execute this. Then the colon right here is effectively the else. So then if this evaluates to false, the conditional to the left of the question mark, we would do this. Okay. All right, that's just in case you're not familiar with that. If the code that's shown at the bottom of the slide seems easier for you to understand, feel free to use that. Okay, but we don't have that much space on the slide, so we'll use the more compact version. All right, so this is the code, which is the same code. Well, not the same code. The same logic that we had when we were looking to sort to merge two sorted ranges. Okay, except that in that implementation that you saw, it was all using iterators. Here, we're using arrays and indices as pointers, right, for the elements in the array. Usually what I do is I basically write this on the whiteboard and then bring up the other slide from the previous lecture to kind of compare the code, but it's kind of, I tried to do that with the software, kind of failed miserably, so I'm not, but I encourage you to look at that slide, and it was, I think, 3 lectures ago, and compare the code and see how similar they are, because it implements really the same logic. Okay, so you give in C, which is, you know, think of it as our output. I can't write with my finger, so I'll just not even try. Let's give my pen another chance. No. My pen has failed miserably. Just keep it plugged in. And then our input array is A, right here. Oops. Input array is right there. Okay. Then, because these are simple arrays, we have the size for A, right? Because otherwise we don't know how large A is. And then our other input array is B, okay, along with its size, because this particular example is with good old arrays, so we need to keep track of the size. No other way to get the size. Okay, of course, if you are using vectors instead of simple arrays, then you could use dot size, right? And this is one for loop on line 3. Basically starts off all our pointer integers, right? I, j, and k, right? So we need I corresponds to the A array, j corresponds to the B array, and k corresponds to the C array for the output. Okay. If you recall, the performance of this algorithm is on the order of size A plus size B. Okay, basically, it's since we need to, in the worst case, iterate over all the elements in the first input array and all the elements in the second input array, then linear on the sum of both sizes. Okay. Now, what this might be quite different from the previous code that you saw is that the first thing that we're doing is checking if we are done inserting all the elements from the first array into the output array, which is C. Okay, so if we're basically done inserting all the elements from A, which would mean that the I pointer has reached size A, right? So if we've been moving things along, okay, with incrementing I, and at some point I would be equal to size A, then it means that all that remains to be done is insert the rest of the elements in B into C. Okay, because that's what's being taken care of there. Else if, right, in a sense, we're either in one case or the other, this case would be that we actually were done with inserting all the elements in B sooner, okay, than inserting all the elements in A, and therefore insert the rest of the elements from A into C. Okay, if you're already done inserting everything in B, so all you need to do is keep insert. And by the way, I'm using the word inserting, but it's really just assignments, right? Just assigning the value that is in the A array. Should come up with better names for these arrays, better than A, B, and C. And then if I am not done, okay, inserting, right, means I have not reached the end of A, and I have not reached yet the end of B, then it's like the normal situation, right? So it's kind of counterintuitive because the last thing that we're doing in this else, it's kind of what most frequently will get executed, right? Because, you know, the condition on line 4 only evaluates the true if I gets to size A, Then the same deal with conditional in 6. So most often we're actually going to fall to executing line 9 in this if-else statement. And this is the one where it goes through the logic that we just discussed earlier, which would be that if the value in A is smaller than the value in B, the values that I'm currently comparing, then I would go ahead and assign the value that's in A, assign that to C. Otherwise, I'm assigning whatever is in B. Okay. If you recall, this is different from the previous code that we saw with iterators because we are basically handling the cases from line 4 through 7 as separate while loops. Okay. If you go back and check, you'll see it. But this is all contained in the same for loop, so it's a lot more compact and nicer. All right, so that's the code. Let's look at an example. Here we have two arrays as input. We're calling them still A and B, but then the elements are just characters, and then you see the integers for each. Excuse me. The size for A is 4, and then the size for B is 3, which would mean that C would need to be of size 7. Okay? If I can manage it. Ooh, size 7. That's supposed to be a 7. Okay? And so what we're going to do now is basically go over each iteration of that for loop with this specific example. Okay? So first what will happen is all my indices, right, which are K, I, and J, they all start at 0, if you recall from the for loop statement that we saw in the previous slide. Everything starts at 0. Now this is a little bit hard to parse because you have like, K equals 0, and then I equals 0, and J equals 0, but these right here are just what are the current values of I and J and K respectively. Okay, that's all it means. So it's a little bit hard to parse at first, but you get used to it. So at that point, our conditional evaluates to true because I is 0, we're checking this first character in A against the first character in B, and determine that yes, indeed, A is less than or equal to B. This is a lexicographical comparison. So if that is true, notice that the pointer that I'm moving is I, right? I'm increasing I, so now I will become 1. And we have placed down here, we have placed the letter A as the first element in the array C. All right, so that's the first iteration of the for loop. We would then move to the second iteration, which is at that point, I will have increased K because now that we have placed an element in the first slot of C, then we need to move to the next slot. And then we will have increased I, but notice we have not changed J, okay? Because we have not placed the first element of B yet in C. So I still need to compare against that same element still, but I'm going to compare against the second element in A, which is D. Then, is D less than or equal to B? The answer is no. So now I will increment J. So now the value of J will be 1. But before I do that, I make sure that I add the second element or make the second element in C be equal to the first element in B. All right, so now the state of the indices is K is 1, I is 1, J is 1 after this update right here. So now go to the next iteration, which would mean that I'll have to increase K again because what I'm looking to add to C is the third element right here. So K always increases by 1. Okay, it is our if loop, our if conditional inside the loop that determines whether I'm going to increment I or j or both. Okay. All right, so third iteration, I have increased k right here. Then now I'm comparing A where I equals 1 against B where j equals 1. Determine that it is D is less than or equal to D. So the answer is yes. That means that I will be incrementing I. Okay, and I place that third element right there in C. And from then on, rinse, repeat, right? The next iteration, I'm comparing G against D, okay, to determine that not less or equal. Make the proper increment updates for the corresponding indices, and keep going until I'm basically done, okay? So notice that all of these iterations so far, all are oops, well, if I wanted to go back to the previous, let me see if I can jump. Yeah, right? That's the execution of line 9 here, right? All those iterations that we wrote down on the next slide correspond to the execution of line 9 here, right? All of these is the execution of line 9. But now, since I am done inserting all the elements from the second input array, which is B, now we satisfy, I believe it was the first line, the first conditional in the if statement. Or is it this second conditional? Let's go back. Oh, it should be line 6 here. That's what gets satisfied here. Okay. So then at that point, all we're doing is setting all the remaining elements in A and putting them in C, okay, which happens twice because there's 2 elements left. Okay. I have a question that C is passed by reference. In the code that you have here, it is, because this is a pass by reference. Remember, in C++ with simple arrays, by default you pass by reference. Now, in the next version of this code that we'll see, we're not going to be actually passing the output array. We're actually going to be creating the output array within the scope of the merge function right here. Okay. So you'll see that in a little bit. But for this code that you have on the slide right now, yes, it is passed by reference. Okay. All right, so if you're thinking, oh, this is quite similar. I remember kind of seeing an example like this. Seems very, very similar. Again, go back to our lecture on ordered ranges. It's also the union find lecture, if you recall. Like we also discussed union find in that same lecture. And we have a very similar example as this one. Again, the only difference is the code is using iterators, so it's a lot longer code. But the concept is exactly the same. Okay. All right, so this is top-down merge sort. It is recursive. We have our base case, which is basically less than 2 items. And still my pen doesn't work. It's failing. Now this is assuming that we have a merge function, right? This is our algorithm for merge sort with actual code rather than pseudocode. So since this is not pseudocode, we need to take care of the base case, which is, hey, there's less than 2 items. Okay, so there's just 1 item. So all we do is return it. Okay. Then find the mid, okay, which is where we're deciding to split the work between the next 2 recursive calls. And so basically merge on the left-hand side, not including the mid, and then merge on the right-hand side, not including the rightmost element. And that's merge sort, not merge. And then at the end, do we actually merge? Okay. Notice that this merge needs the input array. Okay. It needs where the left section of the array starts, where it ends, which is mid, which is also where the right-hand side would start, and then it would end with the right pointer right here. So this basically looks like this merge sort function assumes that instead of taking as input two separate arrays, everything is contained in the same input array. Okay, so then A kind of looks like mid is somewhere here. And then this is left. Oh my God. I apologize. Please work. Try this one more time. Mid. Can't do a D at all. Mid, left, and right. Okay, and all of this is A, the input array. Okay. So it is a prototypical combine and conquer algorithm. It is a recursive call until array is of size 0 or 1. Okay, of course, when would we get a situation in which the size is 0? Well, when the section of the array that I'm looking at has a number of elements that is odd, right? We're dividing by halves throughout. At some point, because it's odd, then you might have 0 elements in the base case. Okay. And then the merge is what basically does the work, right? One question that arises is it safe to use recursion here? Okay. Anybody care to elaborate on this? Is it safe to use recursion here? Give it 30 seconds on the chat. Yep, that is correct. So seems underrated is on point again. It is safe. It basically, the depth should only grow as large as log n. So not terribly bad. And then merge is basically the last thing that happens. So there's no way that we can actually tell recurse on this. But log n, in terms of number of stack calls, is not that terrible. All right, so here is the merge function. So a different merge function that is the one that we would actually be using right here, right? Oh, so this merge function corresponds to this one right here, right? The other one that we were seeing in the previous slide was called merge AB, right? It was a function that was assuming that A and B were in two separate arrays. This function is assuming that both A and B are in the same array, which we're just calling A, but just the ranges are defined by left, mid, and right. Okay, and this is the one that I was referring to, that we actually create our output array within the scope of the merge function. Okay, so we know the size that we're currently looking at is just going to be size minus left, which is line 2. Okay, so that's n. That's how we know what the size of C should be, which we do create in line 3. So now that we have created C, then the code looks very similar. Okay, in fact, it's the same code as we had in the previous example code, except that now we are contending with mid and left here, rather than having, if you recall, in the previous code, we had size A and size B. Okay. And then after we're done doing that, all that work, which is setting the proper values inside C. Then we would use STL copy to make sure to transfer all the work that we did back into A, right? Because up to line 12, we were storing our result in array C, but array C only exists within the scope of the merge function. So if the merge function ends, C will be deleted. The vector C would be deleted, and so I need to copy all that data back into A, which is passed by reference. So therefore, what was given as an input array after the call to merge function would be a sorted array as output. Okay. All right. Let's see. Yes. Oh, thank you for adding that again. I did mention it when the lecture started, but I think we should say it as many times as we can. Please make sure to sign up your time slot for the midterm exam. Okay. Let's see. What's the point of creating a vector if you're just going to copy it over at the end? Oh, good. So that's actually a good question, but it goes to the heart of whether we would try to make merge sort in place, okay, or actually just the merge function, which is what we're looking at. If we wanted to make this merge function in place, right, we would seek a way to implement this such that we would not create the separate vector C in line 3. But it turns out that is not it's easier said than done, okay? And so basically implementing merge in that way is kind of out of scope of what we discuss here for merge sort. We're assuming that we do have enough extra memory to do this and go with this easier implementation of merge sort, okay? But yeah, what the question that was asked basically is the same as asking whether we can do merge in place. The answer is yes, but we're not going to be discussing that. All right. So what's the runtime of merge sort? Not hard to see that it is also an n log n. We've also said it before, so no surprise there that merge sort is an efficient n log n algorithm. Another nice thing about it is the fact that it's stable, right? If you recall, neither heap sort nor quick sort were stable, right? And of course, the important stability is relative to, I guess, the context of what we're sorting. Oftentimes, we really don't care about stability, so it's completely fine to use heap sort, quick sort. But when we do care about stability, then we will have to fall back to a stable sort like merge sort. Okay. It is normally implemented to access data sequentially. This is the same example that I alluded to earlier, which is, say that you have to sort terabytes of data. That's a good use case for merge sort. Okay. It also, if you recall from what we've discussed so far in code, there's really no need for random access. Okay? If you look back at the code, all we're doing is moving to the next element in the array, which if it was a linked list, is just about moving to the next element in the list, right? We did not ever jump in the code to try and find a specific element by using pointer arithmetic, right? Or just, incrementing indices by 5 or something like that, right? We were always just incrementing the indices by 1. Okay. And as I pointed out earlier, it's particularly well suited for parallel sorting, right? Or sorting in a distributed fashion, because it's what we call a problem that can be made embarrassingly parallel, which just means that whatever nodes I'm assigning a specific task in terms of, hey, sort this big chunk of data over here, that node, and by node I just mean a server or a computer, right, can work independently, completely independently from all the other nodes that would be looking at a separate chunk of data, right? So that's what makes it embarrassingly parallel. Okay? I was wondering, why would you create an array and then copy and delete rather than just pass in array? Passing an array seems like it would be much more efficient. I guess that's a matter of style of, I guess, what you would assign merge to do, whether it would create the output array or not, or whether it's kind of the scope of merge sort that it should create the output array and then pass it to the merge function. Matter of style, performance-wise, it would not make a difference because whether you create the output array in merge sort versus the merge function, you still are going to incur that cost, which is what we would care about. Okay. Essentially, you need to know what was in an array as you work. If you overwrite data in the array as you go, you risk getting stuck. Yes, that is true. That's what makes it quite tricky. It's doable, but quite tricky, and really we don't want to introduce any more complexity into the algorithm as we discuss it in this course. Okay. But of course, the topic of conversation has been that extra memory. That's one of its sort of downsides. Okay, it's linear in the amount of additional memory that it uses. Quicksort, so in the last lecture, is actually in place. Then even in the best case, is quite slower even more than elementary sorts, right? If merge sort gets as input a set of elements that's already sorted, it's just going to do the same amount of work, right? It's not adaptive. It will not check or not do anything more efficient if the input array is, as we've been saying before, close to being sorted, right? Or somewhat ordered. So typically that kind of makes it slower than quicksort for the most part. So bottom line is, if you're not sorting ridiculous amounts of data and you don't care about stability, right? So it's okay to use an unstable sorting algorithm, then you should pick quicksort over merge sort. Okay. In practice. Cool. Let's see. Why do we want to sort linked lists? We can't binary search. Yes, but think about it. Going back to the use case, is a question from Henry. If you think back of the use case where we're trying to sort terabytes of data, right? We are also most likely not looking to do a binary search on such a large data set, right? Because on such a large data set, it still might not be as efficient as we would need, right? We would go to other mechanisms rather than binary search. But there's often times where what you need to sort is represented as a linked list, and in that case, like if you need to sort the data, and you have no choice because it is given as a linked list, then you need a sorting algorithm that works there. That would be merge sort. Okay. And again, for example, if you cannot fit your entire set of data in memory, you cannot use quicksort at all. There's no version of quicksort that makes it highly parallelizable like merge sort is. Okay. Again, quicksort relies on random access of the data. Right? If you recall, when we were doing partitioning and swaps, we would need to be able to, swap things in the middle of the array. That's fairly easy when it's an array and everything's in memory. But if you're looking at terabytes of data on disk, right? That's not the case. You don't have random access, right? And so if you represent that data using linked lists, then you'd have to fall back with Mergesort. All right, so let's look at another version of Mergesort. And this one is more bottom-up, okay? And because it's bottom-up, it's not recursive, okay? So another way to look at this is an iterative version of Mergesort, as opposed to a recursive version of it. And so this is called bottom-up because what we're effectively looking to do is you scan through the list. Oh, use the finger again. Scan through the list, performing one by one merges to produce n over 2 ordered sublists. Okay. Then you do the same. So you scan through the list, performing 2 by 2 merges to produce n over 4 ordered sublists. Right. So conceptually, it's doing the exact same thing as the recursive merge sort that we saw, except that now we're using these two nested for loops right here, okay, to look at the proper chunks of the array that we're eventually going to merge together, okay? So if you look at the exterior or external for loop, which is in line 2, this is the current size of the sublist that I'll be looking at, right? And that's on each iteration we do size times equals 2, okay? Because again, if we're looking at halves each time of the array, then the size of what we're looking at should be starting at 1, then increasing times 2 each time. And then the internal for loop, which is line 3, is trying to look at where in the range of the input array A is it that we're going to look at for each one of the, say, 1 element sublists followed by all the 2 element sublists followed by all the 4 element sublists, right? So the internal loop is what basically going to give you the indices to look at. Okay? So again, this is harder to explain, rather just look at an example. I think this is the same example array that we had as input earlier, except now we're looking at the bottom-up or iterative merge sort. Okay. So here, what we'll do is effectively, by way of the first iteration here, where it would look at each one of the elements of size 1, then basically create all these, create all these sublists on the second iteration of size 2, right? And then merge each one of those individual elements, okay, to then form these 2 element sublists. Then the same in the next iteration of the outer loop, which would be this line right here, is when we would go over that internal loop on line 9, and then effectively make the merges of the 2 element sublist to form 4 element sublists. Okay. And then lastly, the last iteration of that outer loop, which would be here, would look at the 2 4 element sublists that we have to form a complete sorted range for the input array. Now, it's the actual specific of how these indices work is, very error prone, right? In a sense, it's very hard to get right, or conversely, it's very easy to make a mistake with how you look at the indices, how you make your proper jumps here versus your proper jumps right here. Okay, we don't expect you to remember all of this off the bat. This is just for your benefit to understand that there's another implementation of Mergesort that is not recursive. It is trickier to implement in that sense, but it is doable. And this specific version has the benefit that it does not incur, right, extra stack frames in the recursive calls because it's all iterative. But conceptually is doing the same thing. And this is also using the same merge function as we were using before. Okay, so basically the job of the nested for loop is to replicate the recursive calls to get to the point where we now get to the base case of single elements that we merge together, right, into 2 elements per list. Okay, then it looks at the next case where we take all those 2 element lists, merge them into 4 element list, and then finish. All right, so that's the iterative or bottom-up merge sort. All right, here's an interesting Java interview question, which again kind of goes back to a use case in which you have more elements that you can fit in memory. So what do you do? And in fact, we say that this is a Java interview question because it does come up often, right? I know I've interviewed candidates in which, if we've solved the problem and, we get to the point where we kind of want to have a more challenging discussion or more interesting rather than challenging, is like, well, your algorithm works completely fine if everything's loaded in memory, real easy. But what happens if you can't have all that data in memory? What do you do? And so if I ask you that we had 100 million elements, how would you find the most frequent element? Anybody care to offer a quick, we have time, so anybody offer a quick potential solution while I read some of the chat messages? I wonder if underrated is staff. All right. Anyone? I'll give it 10 more seconds. If not, I'll give you a solution. So the obvious solution is that probably uses too much memory to do a counting sort. Yeah, well, if we haven't added the constraint that the number of keys is countable and of reasonable size, you can't do counting sort, right? So we haven't added that assumption here, so we would not be able to do that, but it's a good thought. Sort and then go through adding to a count as long as the next element is the same as the previous and find, yep. So we've been discussing merge sort, and we said that merge sort has a particular use case for ridiculous amounts of data. So I would just merge sort and then iterate, basically keeping counts to find out which element is the most frequent. Okay. Right. So that's that's a potential solution. So use merge sort. Now, if we added some constraints to this, we could get faster runtime, right? If we were doing merge sort, that means it's at least n log n time for that solution. But of course, if you recall now, I wasn't, it's a previous lecture that we had. Well, I might have not done that lecture, but if you've been attending our lab lectures, you remember Moore's algorithm. I don't recall in which context we might have. I know I discuss it every time I do this course. I just don't remember which lecture it is. And since this time around, we're only doing like one section of the lectures. Anybody remember? Can somebody point out if you remember discussing Morse? It's basically under the assumption that the most frequent element, so frequent most, oh my God, I still need to write and I can't. So I'm just going to write F for frequency. If frequency is greater than n over 2, where n is, in this case, 100 million. Okay? If you know for a fact, before you look at anything in this data set, if the most frequent element occurs more than is half the time, right? So its frequency, it's really, really large. Then you can use Moore's algorithm and just, this makes it linear time, actually. So this would be with Moore's. That's supposed to be the name Moore's. Okay? And then more generally, if you had the frequency being greater than n over k, okay, there is an algorithm that's called Misra Grice, or Grice. I've never figured out exactly how to pronounce that second part, but I wish I could write it on the slide. Again, apologize. I'm using my finger because it's my pen work again. No, it does not. Well, that's not that bad. Misla agrees. Okay. If you know that the most frequent element is at least n over k times repeated, where k is just an arbitrary constant, then you can use that algorithm, and this gives you an O of n log k runtime. Okay. Can you think of any approaches that could achieve, without really getting into specifics, what could you think of that should be used in the context of an algorithm that knows that the most frequent item appears at least n over k times? Okay. Anybody? And k, by the way, k we're assuming is a constant, and we're also assuming that k is much, much smaller than n. Can anybody suggest a data structure that should be involved? I guess it's a data structure that we haven't yet seen in lecture, but will soon after the exam. But some of you have asked in office hours. Yeah, I knew. A map. Yes, so Henry got it, a map, but I do see how first thought would have been a priority queue. Since in project 2, the answer to everything is use a priority queue. I mean, not to everything, but to a lot of things. But that's a map, or in other words, a hash table. Okay, which I think somebody just pointed out on the chat. Okay, so if you know that the k is, if you know that k is effectively bounding the most frequent element, then you can make use of a hash table to keep track of, instead of the frequency of all n items, right? Only k items, if you will. Okay. It's kind of, depending on how you implemented project 2, you're actually doing something similar to how the Mr. Gray's algorithm works. Okay. Except you're not necessarily using a map in project 2. You might be just using a vector or a deck. But this concept of basically, if you're given, some constant value for the stats, then your container, you just got to make sure that at all times it remains of that size, right? So you don't want it to be any larger than k, where k is whatever we give you for the stats, right? Mr. Grease has the same concept, okay? Not a hash table, but in project 2 you don't use a hash table, but very similar concept. All right, so merge sort is definitely not as involved as quick sort. It's rather simple. It has a particular use case, or several, right? We discuss if we need an efficient sorting that is stable, or if we're looking to sort ridiculous amounts of data that we cannot fit in RAM. Okay, so two potential use case to use merge sort, and we've, here are some study questions, but I feel some of them we've already answered throughout the lecture, which is, can merge sorts be implemented on linked lists? The answer is yes, right? Because you don't really rely on random access. If you look back at the code, all you're doing is moving the indices, which would be just as good as moving pointers. No random access needed means that you can sort a linked list using merge sort. Can the merge step be done in place? We also discussed that. It can. It's a bit trickier, and it can lead to a lot of bugs. So I encourage you to look it up, but we won't discuss it in this course. As far as the exam goes, if we talk about merge sort, we're talking about the version that would use extra memory. Okay, so it uses linear extra memory. Doesn't it need to know the mid index? But it needed to know the mid index just to know where the edges of the right hand side of, let me go back there. So good series. Why no random access needed? Doesn't it need you to know the mid index? Let's go back to that. Well, let me use my. So you see here where we use mid, that is the mid here is used to know where the left hand side ends and where the right hand side begins. Okay, but if you look at this code, we are not doing a mid. We're not doing that, right? That should be correct. So it means that yes, we're using mid, but we're never trying to access and jump to that mid element. Mid is just an integer to determine where the boundaries are for the left hand side and the right hand side that we're looking to merge, right? Because in this version of the merge function, both input arrays are really in the same array, which is A. Make sense, Carson? Yes? No? I'll wait for it while I jump back to the questions for self-study. Cool. Is there a way to make, good question, is there a way to make merge sort adaptive? Well, I think this goes to the last bullet here. How can we improve? Okay. It's given the question, why is the best case complexity of merge sort worse than linear? That we kind of also answered it throughout the lecture, which was like, well, even if the input is sorted, merge sort doesn't know about it, so it would go through the same amount of work, right? Even if the input is sorted. And so how can that be improved? Well, one suggestion would be, which we've kind of thought about this even as we were discussing elementary sorts, you could go through the input and see and have a metric for how close to sorted it is, right? And if that's the case, fall back to a different sort rather than using merge sort, okay? But how merge sort itself can be improved or made more adaptive, I honestly don't know. I have not thought about this, and I actually have not seen any sort of implementations around making merge sort adaptive. Okay, I think it's largely because merge sort has, again, it's kind of specific use cases, and so I don't think there's as much body of work to try to optimize optimized merge sort as there is for the other efficient algorithms like radix sort and quicksort. Because again, you would really use merge sort if you have to, right? Because otherwise you would go to more practical like quicksort, because in practice it's faster than merge sort. And of course, you would not want to incur the extra memory unless you absolutely have to. But a good question. I encourage folks to look it up. Can merge sort be made adaptive? Okay, it's not something that we would, quiz you in the exam, but would be interesting to know. Which sorts don't work on linked lists? Okay, yeah, that's a good question. I'll post it to everyone and see if somebody can come up with an answer for that. If not, we'll talk about it. So again, which sorts don't work on linked lists? I.e., I think, which can't be changed to not rely on random access. Okay, well then at least Henry, is kind of answering it partly and then kind of raising a different question, right? So to the question, which sorts don't work on linked lists, you would say any sort that needs random access would not work on linked lists. You could make it work on linked lists, but then it won't have the same runtime, right? Because if random access, instead of being constant time, is now, say, linear time, then it will change the runtime of the entire algorithm, okay? So then the question is, which can't be changed to not rely on random access? I think all of them you could potentially change to not rely on random access, right? And in fact, if you have an iterator version of your algorithm, okay, you can implement it in such a way that the iterator is not assumed to have random access. And so you go about your code effectively implementing a sorting algorithm that does not use random access. And the problem becomes that if you're not allowed random access, it just means that whenever any operation that would try to be a random access, you would incur something like linear time to find that element in the linked list. Okay, so now all the runtimes changes. It's an interesting question. How would the runtime change? Okay, for the algorithm if you had to do linear access for what should be random, quick, constant access. Yeah, insertion. I would imagine that time, memory, complexity of size, constantly having to rewrite links as you shift everything around would open the door to loads of bugs. Well, that can happen. So this is what I was alluding to with, if you're using iterators and you know all the code that you write, right, assumes that the iterator itself does not have random access, then you kind of force yourself to not introduce potential bugs in what underrated one is suggesting, which is potential bugs in kind of moving the nodes in the list to potentially get to the right position, right? All of that would be handled by the iterators themselves, right? The issue becomes that, for example, STL would not guarantee that that is all of one operation because it's not a random access iterator. And so behind the scenes, it would have to incur linear time to do whatever you're telling it to do, right? If you're telling it, okay, jump to the nth element, right? If you were using a random iterator, then that operation is just going to be constant time. But if it's not a random access iterator, then behind the scenes, it will occur the linear time to get to that specific element. Does that make sense? All right, so we have roughly 8 minutes left. We can just give you back those 8 minutes. I'm sure y'all got either Project 2 stuff. Remember, exam's next week. Make sure you're signing up for it. We do have plenty of review sessions. In fact, the next live lecture on Tuesday is a review session, if you will. Will be headed by Professor Darden, so you'll have the benefit of his lovely voice when he's speaking. Every time he's talking, I'm enthralled by the tone of his voice, as opposed to mine. I'm sure you're all kind of annoyed by my tone of voice, but he'll be starting lecture for his duration of, I think, 6 lectures is what we're each lecturing for, in terms of these live lectures anyway. So it'll be review session Tuesday, and then the exam. Do not quote me because I haven't checked the latest version of the calendar, but I believe we do not have lecture on Thursday. Okay. Oh wait, what am I missing? Is it the week after? Oh, yes, then don't quote me on anything that I said. Let me actually just look up the calendar. Well, I'll let you, actually this is giving me, my software for streaming is kind of a pain. So I'll let you just, so if, yeah. Oh, sorry about that. I might have scared, what is it? Well, I think earlier it was 90 something. Hopefully the 10 or so people that dropped did not leave thinking that next week I might have had my weeks crossed. Might have had my cancel. Maybe I'm still lecturing next week. I'd have to check. Let me just check it right now because there's 80 of you and I don't want to. Sorry, I'm looking here. And we're done with material for today, so feel free to drop. Let's just clarify this, and we should be done. And master schedule. Midterm exam review is on Thursday. Yes. So, oh yes, there is one more topic. So, which is strings and sequences. Completely forgot about that topic, which is how I assumed that the next was going to be the exam review. My apologies. So I think for the lecture on Tuesday, which is October the 13th, you will have Max. My apologies, I screwed all this up. So Tuesday, it'll be Max. And then Thursday, it'll be Marcus with the exam review. And then the midterm exam is on the 21st. Sorry, it's just pandemic calendars are a pain to keep track of. All days blend in. So, I mean, I'm having the same issue at my current work. I mean, this is also my current work, but my other work. All right, so cleared that up. Exam is on the 21st, so you actually have one more week. Sorry if I, caused some people a heart attack. Hopefully, lecture on the week of the 21st. So the 21st is the actual midterm exam. And then Tuesday, the 20th, is we do not have a lecture. Cool. So glad I cleared that up. Apologies for scaring you for that. But that's it for today for the most part. Yes, lecture today is pretty much over. We went over Mergesort. That was today's topic. So feel free to drop. I was just taking care of questions and Um, all right, everyone. Have a great weekend. See you all around at office hours and Q&As and such. Signing off for the day. Take care. Oh, wait. One last. Is there a resource with all the sorts? I would say we do in the review session go over kind of examples and important points and properties about each of the sorts again, including elementary sort and efficient sorts. We also have the lectures themselves. Remember, we had one lecture dedicated to elementary sorts, one lecture dedicated to quicksort, and the other lecture dedicated to Mergesort. And the heap lecture was also included, heap sort. So those lectures, I would say, should be your primary source of information, I guess, for studying the sorts for the exam. And then labs as well. Yeah. But I guess whether there's a single source, I guess what you're asking is whether there's a big summary. I don't think we have that, and that would be it's a good note, an interesting thing to have. Or maybe we do. I don't know if the staff that's on the chat knows whether we do. I would encourage you to post such a request on Piazza, and then we can take a look at that. If we don't have it, if we have it, we'll post it for you in Piazza. If we don't have it, it's a good note for us to have to add in. All right. Take care, everyone. Signing off. Bye-bye.